Hello, my name is Evan Beckmeyer, and today I will be explaining to you the Coriolis Acceleration. Coriolis Acceleration is not entirely a real acceleration that is experienced by an object. Not the same as if a rocket is taking off, it experiences acceleration. It is acceleration that we fabricate to understand movement of objects on a rotational reference frame. What I mean by this can be clarified a bit by the way that the textbook defines Coriolis acceleration, which is an acceleration of an arbitrary point B as measured from a non-rotating and rotating axis x, y, and z. And that just means that it can be done for circles, it can be done for spheres like the Earth, it can be done for, there's a hotel name called the Radisson, and the top actually rotates. It's a spinning restaurant. It's kind of interesting. Any kind of rotational frame of reference can be applied using the Coriolis acceleration to help us understand it a little better. So going back to this restaurant, I've got a little example set up. So if two people, if you think of this as a top-down view of the restaurant, if one person was seated over here, this is a little situation, and another person was sitting over here at this end, and I don't know, maybe the orange person doesn't like the way that the red person's looking at him. So what the orange person says is, I'm going to throw my entire meal at this person sitting at the red table. So what this person's going to have to do, if this was not rotating, would be just use a trajectory straight across like that. Now, this is where the Coriolis acceleration comes into effect. Since this is rotating, let's say this way, if this person throws it directly across, it's not going to reach the red person, because by the time that the food would reach that person, the red table could be over this way, could be here, depending on how fast it's rotating. So in order to counteract that, they could use the Coriolis acceleration to make a little equation to see where it would go. And in reality, it would take some kind of trajectory, probably like this right there. It would kind of have a little bend because the acceleration acts normal to the direction that it's traveling. So if it was going like, if it was pulling this way, then it would cause the trajectory to change as it traveled. So they would have to account for that. From a mathematical standpoint, the Coriolis acceleration looks a little something like this. I'll go ahead and zoom in, where a sub b is the absolute acceleration of b. A sub a is the absolute acceleration of the origin of the xyz frame. Omega dot cross r sub b in respects to a is the angular acceleration effect caused by rotation of x, y, and z frame. We have omega cross or times omega cross r sub b in respects to a is the angular velocity effect caused by rotation of the xyz frame. And this is where the actual Coriolis effect comes into play. This is an equation for acceleration as a whole. So if you did want to take into account, this is our fabricated acceleration right here. 2 omega cross velocity of b with respects to a on the xyz frame. It's the combined effect of b moving relative to xyz. And a acceleration of b with respects to a on the xyz. It's just the acceleration of b with respect to a. So that's how we can think about this mathematically. Excuse me. So a good way of thinking about this, this might not help you all that much visualize it. So there's a really good video that I was able to find online. So I will show you this. This is property of Eduardo Garcia. So here it is. I'm going to go ahead and play this for you. So as you can see, there's these balls coming down. If I pause this at just the right time, all right, you can see that the hole here is not aligned with the chute that the ball is coming out of. So if you look at it from a stationary reference frame of this rotating spindle right here, it looks like the ball is traveling in an arc, when in reality, the ball is traveling tangential to the way that it was released. So that's how the Coriolis effect is. You can maybe think of it as fabricated, not really a real acceleration. because the ball is not actually rotating in that kind of weird manner. And a really good example of this is the Earth. We have to use the Coriolis acceleration to visualize a lot of the effects of Earth's rotation. And one of the best ways to do this is with something we actually have on campus called the Foucault pendulum. Now, the pendulum, you can actually see it on campus. It's at Miami. And at anyone who's passing by, you might just think this is a regular pendulum, but as time passes, you'll notice it is a clock. It can tell the time of day. Now, it's not doing this by any mechanics up here in the ceiling that I'm showing right now in this video. No, it's actually the rotation of the Earth that is causing the pendulum to move.